All right, well, hello everyone, and welcome back. This is our third video on linked lists and node-based data types. And so we will conclude our discussion of linked lists by learning about how we can create different kinds of data structures. This course is an introductory C++ course, so here we're just scratching the surface of data structures. If you choose to take more programming courses, you will most likely take an entire course on data structures. So here we will introduce some of those concepts that you may see in your future courses. If you haven't already done so, please make sure that you have watched our previous two videos which introduced linked lists and also explained how to insert and manipulate the nodes of our linked list. You'll definitely want to be familiar with linked lists as you review the topics in this video. So here's our goals for today's video. First, we will briefly review some of the topics we learned previously, including how to manipulate nodes in a linked list, and also how to use these nodes to build different kinds of data structures. We will also briefly review how to search, insert, and delete nodes from a linked list. Remember, if you would like further review, you can also check out our previous two videos. Finally, in today's video, we're going to focus on using functions and classes in order to manipulate linked lists. In particular, we are going to look at how to build a stack and a queue data structure. Finally, we'll review some helpful hints about how to create data structures, and some of these hints may be useful in our assignments as well. So before we move on, let's briefly review a few key points from our previous videos. One of the most important tools to use when building data structures is the arrow operator. You'll remember that the arrow operator combines the actions of the dereferencing operator and the dot operator. So we saw that we can use the arrow operator in order to go where a pointer points and manipulate data stored within a given node. For example, here, if we have this pointer named head that points to a node containing an int value data and a pointer named next, we can use the arrow operator to set head's data value, where head points to 23, and we can update the next pointer where head is pointing in order to point at null. So for the purposes of this course, you'll definitely want to make sure you know the following linked list operations. So if you would like some review, see our previous videos for additional review of these topics. By now you should be fairly comfortable using the arrow operator and what we know about nodes in order to perform the following basic operations. One especially important operation that we use with linked lists is inserting a node. You'll remember this is one of the big advantages of using a linked list instead of another data type like an array. In a linked list, it is very easy to insert nodes at any location, provided that we do so using the correct procedure. Remember, when inserting, the best practice is to first connect your new node back to your existing list. Once you've completed that first connection by making this pointer point at the location to insert, Then you would want to update your existing list's pointer to point at the new node. The reason that we need to follow these steps in order is because if we reverse the order of these steps, we would actually orphan some of our nodes or lose access to them. Remember, whenever you're manipulating nodes of your linked list, you need to maintain some connection between your head pointer and all of your nodes at all times. If you make a pointer point somewhere else, and you are no longer able to access a node with some pointers, then you'll lose access to that memory, and you'll create what's called a lost node. So make sure you remember to maintain contact between the pointers of your list and the nodes that you're trying to insert. So before we move on, let's go ahead and try one last review question, which is really good practice. So in this review question, we are given a linked list with nodes of list node type. So up to this point in the class, we've been using this list node struct as kind of the base struct for a given node. So we're assuming each node contains an int value named data and a list node type pointer named next. Remember that you can actually create these nodes to be any kind of struct or object. You don't have to always call them list node. But let's go ahead and assume that we're using the list node struct for the nodes in our given linked list. So we are given this existing list, and we have a new node where node to insert points. So we have this node, and it contains some int data called value. So value will be some int value, could be anything. We don't know what value is, we just know that it must hold an integer. So in this example, we want to insert that node containing value so that the list will have all of its data variables in increasing order. In this example, we want to write the code which will determine the correct location to insert our node containing value so that the nodes are in increasing order. So in this case, depending on what value is, we need to insert values node so that our nodes stay in increasing order. For example, if this value contained the number 0, we would insert this node at the very beginning of our list in front of the node containing 10. If we had value as 15, it would go between nodes 10 and 20. If value was greater than 30, we would insert it at the end of the list. So our task here is to write the code which will figure out where do we need to insert value so that our nodes are in the correct increasing order based on the data value that is stored inside. So in this case, our task is to write that code where we figure out where to insert value. So you might remember the strategy that we explained in our previous video. We are trying to figure out where to insert our node containing value. So a good practice is to declare pointers. We can actually declare two pointers, one pointer named cur and another pointer named previous. You'll remember we initially start out with pointer cur pointing at head, or pointing at the same location where head points. So therefore we start with cur pointing at the very first node in our linked list. And what we can do here is we can check. We read each node one at a time. Using our pointer cur. And then we can check the value that cur is pointing at using the asterisk. We can, or with the arrow operator, we can check if current arrow data, that's the value of the data where current points, if current arrow data is greater than the value, then we know values should be inserted in front of cur's node. For example, if we had our head pointer and then we were pointing to 10, 20, 30, and if node to insert was pointing at the value 5, then we would know right away if 10 is greater than our value, which is 5, then we would want to insert such that our value 5 was at the beginning. However, what if our value was 15? In this case, current arrow data was not greater than value. So if not, we need to advance cur and prev to the next node. So in this case, current would now point at our second node, and previous would point where cur was pointing. So let's now consider the case where our value is 15. 15 is between 10 and 20. So here, current arrow data would be greater than value, and in this case, we would want to insert our node containing 15 between the 10 and the 20. So as illustrated here, we want to use those pointers current and prev in order to identify where to insert that new node. But then what happens if we reach all the way to the end of our list? Say value contains like 50, or a large number. Well, if we go all the way to the end of the list and we still have not inserted our node, then we would therefore need to insert our new node at the very end of our list. So let's go ahead and try writing out this code in C++. The first step would be to declare those pointers current and previous. So to do that, we just use our node. Remember, we have list node as our struct, so we'll go ahead and define current. So we declare current and we make it point where head points. And initially, previous will point at null pointer, but later we will advance it if required. Our next step is to read each node one at a time. So to do this, we need to use a while loop. As long as current is not pointing at the end of our list at null, then we keep reading. And what goes inside our while loop? Well, once again, our goal is to check whether current is pointing at the location where we want to insert. So we can use an if statement. If the value I'm pointing at is larger than the value I want to insert, then what do? I should break, because this will allow us to exit the loop with current and previous at the desired location. Because once current and previous are at the correct location, then all we need to do is exit our loop and perform the insertion. So what happens if this if statement does not trigger? Well, that means we have not yet found the location where we want to insert. So otherwise, if the if statement doesn't trigger, then we need to increment our pointers to the next node. So in this case, where would current point? If I want to advance my pointer current, I need to set current to be equal to current arrow next in order to make it point at the next node. So therefore, I need to advance current, but before I change the value of current, I'm going to set my pointer previous to point where current points, and then I will say current points to current arrow next. So this way, I will advance my pointers to the next node, and then repeat my while loop until I determine the correct place to insert. So notice that this code does not actually insert the node in the correct location. This code is purely determining where in the linked list we would need to perform the insertion. So this code will simply set up our pointers current and previous so that we are pointing at the desired location. For example, if our node contained the value 25, we would want to insert between the 20 and 30, so we would want to have our previous and current pointers oriented as shown here. So once again, here's an example of what that code would look like. You can see that it's very helpful to use a while loop to step through and check each node one by one until we find our desired location. There's one other hint I would like to share, and this hint comes from some of our past assignments. When inserting a node, you need to account for edge cases. So there's actually a few different edge cases to consider. First edge case is if the value you need to insert needs to go at the beginning. Notice, for example, if we had the value 5, we would actually need to attach 5 to the very first node 10 and then make head point at our node containing 5. So if the value to insert needs to go at the beginning, then we insert our desired value and attach it to the very first node where head points. But then we also have to update our pointer head to point at the same location as node to insert, because head must point to the very first node in our list. So that's the first edge case. Second edge case is if the value to insert needs to go in the middle of the list. Well, if that's the case, it's actually the easiest case. We just follow the procedures that we learned. For example, if we have previous and current here, and node to insert was pointing at the number 15, remember, all we would need to do is say node to insert arrow next equals cur in order to attach our new node to the existing list. And then we say previous arrow next equals node to insert. That would detach previous arrow next's pointer from the existing list and attach it to our new node. So that's our second edge case. And that follows our standard insertion. Finally, we have one more edge case if the value we need to insert needs to go at the end. And the one thing to be careful of there is our last node's pointer needs to point to null. So in this case, if our node that we need to insert needs to go at the end, then our current pointer is actually going to be pointing at null already, and previous is going to be pointing at the location where we want to attach our node. So here, for example, if we had that node containing 50, then we would need to write the code previous arrow next equals node to insert. That would take previous's next pointer and make it point at the node we want. And then we'd need to make sure that node to insert's next pointer points at null. In this case, it already does, but you would want to make sure that you're pointing at null because that node is now the end of your list. So be careful of these edge cases. Sometimes it's easy to forget about edge cases. And also if you have some other variable like length where you're keeping track of how many nodes are in your list, you also want to make sure you update those variables as needed. So definitely keep these hints in mind as you finish up our remaining assignments. And don't be afraid to draw pictures as I did here. Drawing pictures is a really great way to visualize what's happening in these linked lists. Alright, so that concludes our review of linked lists and the basics that we covered in our previous videos. So if you would like extra review, make sure you check out our previous videos which introduced linked lists. and feel free to reach out if you have any questions. We'll now go ahead and finish up with our last topic of the course, which is an introduction to data structures. All right, so up to this point in the class, we've learned about this thing called a linked list. And we learned that a linked list, at least for our purposes, contains some pointer named next, some int value named data, and we have any number of these nodes. And then we finally end with our list pointing at null pointer. And we talked about how this particular data structure is useful if we want to store a list of values, but this is not the only kind of data structure we can make. In fact, there's an entire course called Data Structures that's dedicated to learning about the most efficient data structure for the application you need. Depending on the type of data you're trying to store and how easily you need to be able to access or search or sort that data, different kinds of data structures might be more useful. So this one is just a classic linked list structure, but we can also create other kinds of structures as well. For example, we could, if we so chose, we could create something called a circularly linked list. So instead of having our linked list pointer point at null, we could, have some sort of starting point in our linked list, but we could actually have the end of our list connect back to the beginning. This might be useful, for example, if you're trying to program a menu where the user can loop back to the beginning, or maybe you want to make a board game where you can move around a game board multiple times. There's also things like doubly linked lists, where you can actually have 2 pointers on each node. So if your node contains 2 pointers, then you can move both forward and backward in the linked list. And there's also some really interesting structures called trees, where you can create branching nodes with 2 or more branches, and depending on what you're trying to do, trees can make it a lot faster to sort through large sets of data and perform other kinds of tasks. So depending on the application for your data and what you're trying to do, being able to recognize the right data structure for the job is really important. For the purposes of this course, our goal is to just briefly introduce data structures. So here we're going to focus on 2 main types for this class. First type is called a stack, and the second type is called a queue. Remember, the other types are covered in data structures class. So let's go ahead and first introduce stacks. Stacks are a very simple data structure, but they're also extremely important. In a stack data structure, it behaves almost exactly like a stack of cards or a stack of objects. And basically what happens is that data is retrieved from the stack in the reverse order in which the data was stored. For example, here if I have a stack structure and I store the values A, B, and C inside my stack, notice that if I want to remove the items from my stack, the first item that will be removed is the value at the top of my stack, which was letter C. Then I would be able to remove letter B, and then finally my letter A. So you'll notice that in a stack data structure, we say that adding an item to the top of the stack is called pushing. It's actually a technical term that programmers use. So if you push something to the stack, that means you are pushing it to the top, or you're placing it on the top of your stack. Similarly, if you want to remove an item from the top of your stack, programmers call that popping. So you're popping off the top value from the stack and removing it from the data structure. A good example of a stack data structure is the undo function. If you press Ctrl-Z or undo in a program, it will undo the last thing that you did. And so the undo function actually commonly uses a stack data structure in order to quickly access the previous command so that you can undo it. Often we call these data structures last in, first out data structures because the last item that we added will be the first one that we remove. Finally, you'll notice that the pointer called top will always point to the topmost or very first node in the stack. And if top points to null, then we know we have an empty stack. And believe it or not, it's actually pretty easy to build a stack data structure. We can create a node very similar to the ones that we used in our linked lists. For example, we could choose to create a node called stack node, which contains a data value, maybe an int, and some pointer named link. And so in this case, for example, we could declare a top pointer and make it point to multiple nodes within our stack structure. We'll go through an example of a stack a little bit later. Another kind of data structure that we will learn in this course is a queue data structure. And a queue data structure behaves just like a line of people waiting. So just like a line of people waiting for maybe checkout at a grocery or waiting in line for a service, a queue is a first in, first out data structure. So the first item that we add will be the first item that is removed. Queue data structures are very important in applications such as manufacturing, or in a hospital, or in order tracking. Basically, any time you want to store a list of items in a particular order, a queue can be really important. We also learned in our assignments about a priority queue. So in that special kind of queue known as a priority queue, it's even possible to hold the items in the queue in order of increasing or decreasing priority. So typically in a queue data structure, you generally always need a pointer that points to the front of the queue, but you may also want to have a queue where you have a pointer at both ends. So sometimes you will make a queue that has both a tail pointer that points to the back, where we add items, and a second pointer named the head or front, where the items are removed. So the technical term for adding items to a queue is called enqueue. So for example, here you see if I add A, B, and C, I can say I'm enqueuing A, then B, and then C, and you'll notice the first item we add is at the front of our list. Then if I want to remove items or dequeue them from my queue, you'll notice that the item at the front of the queue, or at the head, is removed first. So first my letter A is removed, then B, then C. So a queue is a very useful data structure if we want to be able to easily add items to the back and remove items from the front. And you can see that the way to create these queues is actually pretty straightforward. We can declare our own node that contains some pointer and some data, and then all we need to do is use the arrow operator and the tools we know in order to create head and tail pointers and link our nodes together. So we'll take a closer look at queues in just a little bit. Finally, before we move on, I'd also like to introduce a few special types of node-based data structures. So, just an FYI, I don't expect you to know these for this course. But if you do take more advanced programming courses, such as data structures, you'll actually spend an entire course on data structures. And you'll find that it can be an incredibly challenging and very important problem to design and develop the right kind of data structure for the job. So, as we hinted at before, there are many types of data structures we can build. In a doubly linked list, our nodes actually have two pointers, often called previous and next, and so this allows us to be able to travel both ways in a linked list. Also, the tree data structure is very interesting. In this structure, we have our nodes able to point at different branching locations. There's also a special type of tree called a binary tree, where each node always has two pointers that point left and right to other nodes. So you can imagine, depending on whether you want your data to be sorted or unsorted, or if you want to be able to search quickly within your data structure, sometimes one of these data structures will be more efficient than another for a given task. So a very important part of programming is designing and developing the right data structure to hold your data and enable you to do what you need in the most efficient way possible. So if you take a data structures class or more advanced programming courses, you'll get to learn more about these and other kinds of data structures. But for the purpose of this class, I only expect you to know about stack and queue data structures for now. So let's go ahead and do a couple demos of a stack and a queue data structure. Then, to help everyone practice, we'll try coding up a few of the actual functions that enable the stack and queue data structure to work. I highly recommend that you follow along with these demos and draw pictures as needed in order to understand what's happening. It's really good practice to try implementing these data structures from scratch and verify that you're able to get the same result as I did. Let's go ahead and start with an example of a stack. In this case, I have a very simple program, and this program uses a stack to store a word. So we prompt the user for a word, such as hello. And if I were to store the word hello inside a stack, notice the H would be stored first, and then the O would be inputted into the stack last. So if I wanted to go back and retrieve my word from the stack, notice I would actually output my word backwards. because in this case, I actually am retrieving the very last letter first. So real quick, let's go ahead and demonstrate this example stack program. And after we've demonstrated it, we'll try coding up a few of the functions on our own. So in this example program, we have a main function where we declare an object of stack type. So you can see in this main function, we're prompting our user to enter a word, and we use cn.get in order to read each character from the word one at a time. We use a while loop and the push function of our stack class in order to add each character one by one into our stack. Then, once we have added all the items to our stack, then we use a second while loop to read through our stack, and as long as our stack is not empty, we use our pop function to read the item from the top of our stack and output it to the screen. So this allows us to store a word inside our stack and then output that word backwards to the screen. Finally, we ask our user if they want to enter another word just for fun, in case they want to try outputting another word backwards. So if we go ahead and run this program, you can see what happens. We enter a word. For example, we can go ahead and say hello, and we see that written backwards, we get hello. I'm going to try again with another word. And notice you can even do a sentence in this case because we're reading one character at a time. So you can actually read a whole sentence backwards. If we finally say no, then our program ends. So this was just the main function that used our stack class and stack objects. If we look inside our stack class, we see that we actually did use some constructors and destructors, and we also needed to declare and implement the push and pop functions in order to add things to our stack and remove things from our stack. We also used an empty function, which returned true if our stack was empty. Sometimes this function is also called isEmpty. Finally, since we're using separate files to implement this class, we have an implementation file, stack.cpp, where we put all the different definitions for each of our member functions. So just for fun, and for extra practice, let's try going through and coding up some of these implementation functions ourselves. This is really good practice to make sure you're comfortable with linked lists. So now that we've seen our stack example and our header and main function, let's try practicing writing some of these function definitions. So in this case, we're being asked to write the default constructor for our stack class. And if we look back at our function declaration inside our stack, you can see that the precondition comment here says that our stack default constructor should initialize our stack object to be an empty stack. So this constructor should initialize our stack to be empty. Well, how do we know whether our stack is empty? If you look at our private variables, you'll see that the only private variable we have for this stack is a pointer named top, which would point at the different nodes in our stack. But if our stack is empty, where would top point? Well, in this case, if our stack is empty, our pointer top should just point at null. Also notice we do not redeclare top here, so we do not say, for example, stack node star top points at null pointer. Remember, that's not correct. We do not need to redeclare our top pointer. Instead, we just want to take the existing top pointer that our object already has. So we're going to take our current object's top pointer and we make top point at null. If our top pointer points at null, that means that there is nothing in our stack and top is pointing at the null memory address. You'll also notice that we chose to put our struct declaration for stack node inside the private part of our class. This is often a good practice because we don't necessarily want other people to mess with what a stack node should be. We want to keep that information hidden so that only our member functions can actually create and use stack nodes. All right, so let's now try another one. In this case, we have our function empty. As noted in our postcondition comment, this function should return true if our stack is empty. Otherwise, we return false. All right, well, how do we know whether our stack is empty? This is actually a very easy function to write. Remember, if top points at null, we are empty. So if you want to write this function using a single line of code, an experienced programmer would actually write empty like this. Because we know top double equals null pointer, this will return true if top points at null. Otherwise, it will return false. It would also be acceptable to just use an if-else statement here, but you'll see that seasoned programmers will often just use a single line of code here because this single return statement does the same thing as that if-else statement would. All right, let's try another example now. Suppose we want to write the function definition for this function push. Remember, what push will do is push is going to add a node containing this value new char in the argument, and it's going to add that node to the stack. So if we already have a stack containing, suppose we have 2 items, and we say, suppose we want to push a node containing the value 5, then our result will be we're going to create a new node that holds the number 5, and we are going to insert it at the top of the stack. So therefore, this function needs to basically do 2 things. First, we need to create our new node containing the value we want to push. And then our second step, after we've created that new node, then we need to insert the node where top points. And remember, top will always point to the very beginning of our list. And then finally, our last step, we need to update our pointer top so that it points to the very first node. Because initially, top might actually be pointing at our second node after we attach our new node. So we have to update top, make sure top is always pointing to our very first node. So let's go ahead and give this a try. Our first task is to create a new node containing the value that we want to push. To create a new node, we first have to create a pointer that points to that node. So I'm going to go ahead and just create a pointer of stack node type. And I'm just going to go ahead and call my pointer new node. And I'm going to make that pointer new node point to a new stack node struct. So what this will do is this is going to create a pointer named new node that points to a stack node struct. My next step is I need to update the data inside my stack node to contain the value I want to attach. I want my new node to contain the value new char in the data. So how would I update the data value where new node points? To update that data value, I need to use the arrow operator. New node arrow data needs to be set equal to new char. That way, whatever value I put in this push function will be stored inside data. So if I say push 5, that would store the value 5 inside data. Then initially, I could decide to make my new node's next pointer point at null initially. But my next step is to insert this node where top points. So I want to insert my new node where top is pointing so that that node will now be on the top of my stack. So where do I need to make my next pointer point so that I will insert my node where top points? Well, in this case, I need to make my next pointer where new node points. I need to make that next pointer point where top points. So this will take my next pointer and connect it where top points. Problem is, when I do that, initially I'll have something like this, where top is pointing at my second node. I need top to be pointing at my first node, where new node points. So what should I update top to be so that it points at the very beginning of my list? at the very top of my stack? Well, in this case, I need to make top point where my pointer new node points. That way, top is always pointing at the top of my stack. And then if I need to add any other stuff to that stack, it would be very easy to do so. So that's it. All we needed to do is insert our new node at the very front of our list and update our top pointer so that we continue to point at our first node. Let's try one last function before we move on. This last function is pop. You'll notice the pop function actually returns a char type value. If you look in our precondition and postcondition, you'll see that pop requires that our stack is not empty. Pop is actually going to remove the top node from our stack and return the character that was stored inside that data value. For example, if I had a stack that contained the numbers 1 and 2, and if I said pop, then that would actually take the very first item in my stack. I would return 1, and then I would delete that node. So I'd return that 1 value, and now my list only contains the remaining nodes. So in this case, we actually have to not only find that node, but we also have to delete that top node from our list and return the value back as the return type of the function. So let's just walk through the different tasks that this function will need to complete. The first thing we need to do is make sure that our stack is not empty. That's very important. Remember, if we try to do something at the null memory address, we will create a runtime error. The next thing we need to do is declare a temporary pointer. We will see that we'll use this temporary pointer in order to access and then delete our topmost node. And then meanwhile, we move the head pointer to the next node. And then finally, we return the value stored in the topmost node to the screen. Or in this case, we return the value stored in the topmost node as the function's return type. So let's go ahead and walk through these steps. First, we need to make sure our stack is not empty. How do we do that? Well, there's two ways. One way is we could use the empty function. If that empty function is already defined, we could just call it and then exit with an error code if we detect we're empty. If we didn't have the empty function, we could just check whether top was pointing at null. Our next step is to declare that temporary pointer and a temporary variable. So in this case, let's go ahead and declare a pointer called temp. So it will be a stack node type pointer. And we're going to make that temp pointer point at the first node of our list. So in this case, I'm just declaring a pointer temp, which will point where top points. Additionally, I can declare a result variable, and I'm going to initialize this variable result to temp arrow data. That way, I can store, for example, here if I have the value 9, I could remember that value later for when I need to return the value stored in that node. Remember, my goal is to delete the topmost node on my stack. So the next thing I need to do is I need to move my top pointer to the second node. So in this case, I'm going to move my top pointer So notice now top is pointing at my second node. And when top is pointing at my second node, that means I can go back and delete the node where temp was pointing. So now I have deleted that pointer temp, but notice I've stored the value that I had there in my variable result. So now all that I need to do is return that char value result where I had saved my data. If I had some variable to track length, I could also decrement length, but in this case, I don't have any variable keeping track of the number of nodes in my list. So all I needed to do was delete my topmost node and then shift my pointer top to the next node in the list. Notice that the order matters. I needed to first move top to my second node before I could delete my first node. This way I still had access to the rest of my stack, even after I had deleted my first node. And in this case, notice that I actually had a small typo here. In this case, I used the name link for my pointer, not next. So in this case, I would write top equals top arrow link, not top arrow next in this case. Same thing here. This one should have also been new node. Arrow, not next, but link. So just pay attention to what name you are using for your pointers and make sure that you give it the correct name. All right, so with that, that concludes our explanation of the stack data structure. And you can see in this slide, I've included an example of what the implementation could look like for that stack data structure. Let's now finish up with our example of the queue. In this queue example, we're doing a very similar thing. We're storing characters into a queue data structure. And so if I have, for example, the word hello, if I put the word hello into a queue data structure and then take the data out, I would actually recover my data back in the same order that I had before. Let's briefly demonstrate this queue example in CLine. All right, so here we are in our queue main function, and you see that our approach is very similar to our stack example. Once again, we are using cn.get in order to read characters one at a time from a user's inputted word. Then we're using an add function in order to add the letters one by one into our queue. We could also use the technical term enqueue for the case where we are adding items to our queue. Then, once we're ready to output our data, we use the remove function, or dequeue, in order to delete each node one by one from the queue and return its value back to our main function. Finally, we ask our user if they want to input an additional word, and we continue running until the user says no. Let's go ahead and give this a try. So you can see here, if we go ahead and enter, for example, hello world, notice if we put that data into our queue, and then we output it back, we get the exact same thing. Remember, queues are first in, first out data structures, so the data is stored and retrieved in the same order. We'll notice that this queue data structure is also built using a queue class, and just like with our stack data structure, we needed to declare and implement various functions in order to make our queue work. And we put all these functions in our queue.cpp file. So let's go ahead and practice writing a few of these queue functions. And this will help us get a little more practice with linked lists and this queue data structure. So once again, we saw that our queue class contains our header function. And once again, we chose to make our queue node struct private so that other functions aren't able to go in and modify that base node of our queue data structure. You'll notice we also have two private variables this time, one front pointer and one back pointer. Sometimes these are also called head and tail more commonly. And these would basically indicate the places where we remove items at the head or front of our queue, and then at the back or tail, that's where we add items to the queue. And then finally, we have a similar approach with our main function and our implementation. Real quick, let's go ahead and practice writing a couple of the implementations for our queue class. First one is our add function, also known as enqueue. All right, so the one thing to be careful about with this add function is we want to add the item to the back of the queue, but there's basically two cases. First case is if the queue is empty. If our queue is empty, you'll remember that both our front and back are currently pointing to null. And the result, if we add an item to our queue, then we would have both front and back point at our new item. The second case, if the queue is not empty, in that case, maybe we already have a few items in our queue. And if we add an additional item, then remember that item gets added at the back. So the procedure will be slightly different, because if our list is empty, or if our list is not empty, then we add the item to the back of the list. And notice in this case that we'll need to update the back pointer so that it points now to the new item that we have added. However, if our queue is empty, we also need to make the front pointer point at the item that we added. So depending on these cases, we actually have two different sets of code to write in our add function. So first we want to check if our queue is empty. So to do that, we could simply check by calling our empty function, or we can check whether both front and back point at null. If both of our pointers point at null, then we go ahead and run the case where we are adding to the empty queue. If instead we find that we are not empty, then we complete the other case where we add to an existing queue. So if we need to add to an empty queue, then all we need to do is we need to create a new node where our front and back pointers point. So we can go ahead and make our front pointer point at a new node. And then all that's left is to update so that all the data is stored in the correct place. So we can say front arrow data equals item, the value we want to store. And then in this case, front arrow next, we'll just have our node point to null because it's the only node in our stack. Then finally, we need to just make sure that our back pointer also points where front points. And in this case, once again, I made that small mistake. Be careful here to use the correct name. In our case, the pointers linking each node together are named link, not next. So let's just make sure we use the name link when we are modifying the pointer within each node. So now we've covered the case where we need to add a node to an empty queue. The last step is to consider the case where we need to add to an existing queue. So if we want to add to an existing queue, we'll need to declare a temporary pointer. And we can make that temporary pointer point to a new queue node. And then, like before, we need to actually update the data inside that new node. And then notice once again, since this is being inserted at the back of our list, we make that new node pointer point to our null pointer. Notice in this case, we need to add our node to where back points. So we need to say back arrow link equals temp. So we need to make our current or make our last node of existing list. We need to make the last node of our existing queue point to temp in order to attach that node at the back of our list. Then our last step is to update our back pointer. So we make our back pointer point at the end of the list. Or at the end of the queue. So definitely keep drawing these pictures in order to keep track of what's happening in our lists. You'll see it's really, really helpful, especially when you have a lot of nodes to insert and remove. Being able to correctly add, remove, and manipulate nodes of a linked list is actually what allows us to build data structures. All right, so real quick, let's just take a look at what the remove function would look like. And so notice that the remove function is kind of similar to the pop function in our stack. And this remove function could also be more formally named dequeue. Often we use the technical term dequeue to refer to removing things from a queue. This is an example of what the remove function could look like. We first check to make sure our queue is not empty before attempting to remove our nodes. If our queue is empty, notice we give ourselves a warning, and we exit. Otherwise, if our queue is not empty, then we proceed with the removal as usual. Notice that we use some temporary pointers and variables to store the node and the data that we are going to be removing. So we use the variable result to store the data from the node being removed. And notice that we also advance front to the second node. So we actually move our front pointer to the next node in the list. Once we've done that, then we can use the delete operator to delete the temporary pointer discard, where we make discard point to the first node at the front of our list. So notice how using these temporary pointers is really important in order to correctly delete things and maintain access to the rest of our list. Also notice what happens here. We also have a little bit of code to capture an edge case, where if we find that our front pointer is now pointing at null, then we know that we deleted the last item in our queue, and then we make both our front and back pointers point at null. Finally, the last step is to return the result, or the thing that was stored in the node that we had removed. So here are some examples of what the implementation could look like in our queue data structure. I highly recommend that you consider going back through these functions, try drawing pictures, and coding these functions up on your own. One of the best ways to get really comfortable with these data structures is to go through and draw pictures and understand how to build and create these functions yourself. This is one of the best ways to get really comfortable and make sure you understand how to use linked lists and data structures. If you choose to take more advanced programming courses like Data Structures class, you'll find that the ability to manipulate nodes with functions like this will be extremely useful. So with that, let's go ahead and wrap up here for today. Hopefully now you can see how powerful linked lists are. and how they can actually be used to build all sorts of unique and interesting data structures. Depending on the type of application you're working on, there's many different data structures that could be used, and part of a programmer's job is to identify the right data structure for the given application. Make sure you understand how to use C++ code and the arrow operator in order to construct and manipulate linked lists. And definitely don't be afraid to draw pictures to keep track of what's happening. As you've seen in our previous videos, drawing pictures is incredibly helpful. Finally, make sure you know how to create stack and queue data structures. Those are the two data structures that you should know for the purposes of this class. But you may learn about other types in future courses as well. So I hope you found these videos helpful, and I hope you enjoyed our time in this introductory C++ course. Thanks so much for watching these videos and for a great semester. In our last video, we will conclude with some sample programs and final exam review. Feel free to reach out if you have any other questions on these topics. Thanks everyone, take care, and I hope to see you in a future course or a future video again soon.